Hi, welcome to this session about regularization in regression. So last lecture we have discussed what regression is. It is the task of finding a function which approximates a number of given samples, which we have given as observations in the data. And we've also discussed how we solve the regression problem. And one of the things which we did not discuss in detail yet was what happens if there are infinitely many regression minimizers and regression functions which actually solve our regression problem. What do we do then? And this will be the topic of this lecture. We have seen that we might get infinitely many regression minimizers if certain properties of the design matrix hold. And the question is now can we just choose any of them, or are some maybe better than others? So first let's recap what we have defined as a regression optimization problem. So here was this picture where you can see a number of samples as the red dots, and then we wanted to minimize the residuals, where the residuals was the distance of the points subject to our target variable y of the function that we are going to use as our approximating regression function. And then we had the following result. So this is the slide from the last lecture. And the result was that the global minimizers of the regression problem are given by this set of regression vectors beta, where every beta determines one regression function. Now, if the matrix X transpose X is invertible, then we can solve this. Then we can multiply the equation above by the inverse of X transpose times X, and then we get as result one uniquely defined optimal regression vector beta. But there might also be infinitely many local and global minimizers of the residual sum of squares. And one of the examples was to fit this polynomial function of degree 3 to 3 observations. Okay, so we had our function f from x, which is a polynomial of degree 3, and then the trick in regression to arrive at our general formulation of minimizing the residual sum of squares was to write our function as an inner product of a function phi, which transforms our features to another space. And this phi from x is then multiplied with the inner product with our regression parameter vector beta. And here in this case, we have phi from x transposed is given by this vector here. And then we have here our silly data. So you see here the first point is 5 and 2. So this would be this point here. So here we have 5, and the target variable is here 2. And then we have 3, 5, and 1, 3, which are also denoted here by these dots. These are our 3 points. And then the next step in regression was to define our design matrix. And the design matrix had these vectors here, phi from x transposed, as the rows. So for every point we apply here our phi to our feature. So here the first feature is 5, and this row is here 5 from 3 transposed, and the last row is 5 from 1 transposed. And then we have our design matrix. And then we had the formulation of the residual sum of squares problem to minimize the residual sum of squares. And then we got as a result that our solutions are given here by this set of regression parameter vectors beta. Now in this case, we have the dimensionality P, which is the dimensionality of our transformed feature space. P is here equal to 4, and we have only n equal to 3 observations. And this is a problem in the sense that a matrix like this will never return an invertible matrix X transposed X. And we can see why by applying the singular value decomposition. We have already seen the singular value decomposition briefly in the linear algebra recap. Now we want to apply this. So how was that actually defined? For every matrix X, for example, here's our design matrix, there exist orthogonal matrices U and V and a diagonal matrix sigma such that X is decomposed as U times sigma times V transposed. And then in sigma we have on the diagonal these singular values which are ordered by their magnitude. So the largest singular value is at the top left and the smallest singular values are at the bottom right. And then you can only have singular values larger than or equal to 0. So the singular value at the bottom right is at least as large as 0. And then we had also this visualization. So this is for the case we have here that p is larger than n. And you see here that we have then this block of zeros, which has a dimensionality of p minus n. And keeping this in mind, we can have a look now what the connection is from SVD to the inverse of a matrix. So SVD determines if a matrix is invertible. And this we also had just briefly in the linear algebra cap. So we have here an n times n matrix A. We can only have invertible matrices which are quadratic. So this matrix A with the singular value decomposition as denoted here is invertible if all singular values are larger than 0. And this is because in this case our matrix sigma has non-zero elements on the diagonal. And if we have a diagonal matrix with non-zero elements on the diagonal, then we can invert this matrix pretty easily by just inverting the elements on the diagonal. And of course, if one of these elements here is 0, then we have a problem because then we would here divide by 0, and this of course cannot be. Now what does this imply now for our regression problem? So we start here with our set of linear equations as is given here for the set of global minimizers beta. And then let's decompose our matrix X and let's try to solve this. So if we insert for X now the singular value decomposition, then we get here for this equality the following. So X transposed is then V times sigma transposed times U transposed. This is X transposed and then times X, so this is then U sigma V transposed. And this we multiply with beta, and then we have here X transposed times Y, so X transposed is V times sigma transposed times U transposed, and then times Y. Now here we have U transpose times U, and U is orthogonal, so this is equal to the identity matrix. And then we can multiply this equation with V transposed from the left, because here we have V on the left, and we want to solve now for beta. So if we multiply with V transposed from the left, then we have the equation sigma transposed times sigma times V transposed beta is equal to, here we have now V transposed times V on the right. So this is the identity matrix, and then we have left sigma transposed times U transposed times Y. So this is what is standing here. And here we do not get necessarily any further, because sigma transposed sigma is for the case that n is smaller than p, definitely not a diagonal matrix which has only non-zero elements on the diagonal. So this is a problem here. We have no inverse for this matrix if n is smaller than p. But of course, what can also happen is that we have less than n singular values. So if we look back at this decomposition here, then we have at most n non-zero singular values here. But of course, we can also have the case that we have here some singular values which are equal to 0. And we denote here with the index r the singular value, which is the last one, which is positive. And the case is now that sigma transpose sigma does not have an inverse if we have r smaller than p singular values which are non-zero. And why is that? So here at the top we have our result from before, right? This is how far we came if we have our singular value decomposition as denoted here. And if only r smaller than p singular values are non-zero, then we have a sigma transposed sigma in this form here. So we have sigma 1 until sigma r to the square on the diagonal, and the rest is all 0. So that means that we have here p minus r columns which are 0, and we have here p minus r rows which are 0. And then we can actually compute something which is called pseudo-inverse. So we take the inverse of all the diagonal matrix elements which are non-zero, and everything else stays 0. And then it's called a pseudo-inverse because it's not actually an inverse, because the equation sigma transpose sigma times the pseudo-inverse sigma transpose sigma plus, as it is denoted here, is not equal to the identity matrix. But we have another property, and that is that sigma transpose times sigma times the pseudo-inverse. And if I now multiply with sigma transpose sigma, that I get again sigma transpose sigma. So this here is not equal to the identity matrix, but it behaves a bit like a neutral element. So if we multiply with this matrix, then we get the matrix itself again. If you want to look up how that goes in detail, then please have a look at the accompanying math PDF. Now, if we take this shape of sigma transpose times sigma and then we calculate a bit around with it, then we see that if we have r smaller than p non-zero singular values, then we have infinitely global minimizers. So then we get one solution for any matrix A, where A is defined as it is given here. So here we have the invertible part of our singular value matrix. And here we have a random part. So this is a random matrix. And for any random matrix you insert here, you get another beta. A bit of a special case arrives now if we define our matrix A equal to the pseudo-inverse from sigma transpose times sigma. So instead of having here some random elements, we have now everything equal to 0, and then we call this solution the solution beta plus, which is the regression solution derived by the pseudo-inverse. And then if we look at our example, then we see that we have here in blue our solution given by the pseudo-inverse, so this is beta plus. And yeah, these are some other samples we got, so this is beta 1 and this is beta 2. And because this was now a bit abstract, I wanted to show you how that goes in practice. So we have here our absolutely nuts data set, so it's just far too small, but it's a good toy example. Now we want to fit our polynomial of degree k, so this is our function phi from x, and then we implement here phi from x. And then we formulate our design matrix, so here we have phi applied to all the rows of D, and then we have to transpose it because, yeah, this was the definition of the design matrix. It has always the transposed function values as rows. And then we can now go ahead and just try to solve this, right? So this was the set of our global minimizers. So we solve here for the beta, which solves this system of linear equations. And then you see that you get here a warning, and it says ill-conditioned matrix. So we get here some solution, but we don't know if that's correct or if it's good. You might want to have a bit more control. So let's do what we have said in the lecture. So we calculate the SVD. This is with the sci-fi linear algebra package. And then we get our matrices U and the sigma, which are our singular values, and V transposed. And you see here the shapes. So U is a 3 times 3 matrix. Then the sigma is actually just the singular value, so it's just an array. And we have V transposed as our 4 times 4 matrix. And then R is our index, for which we have actually non-zero elements of singular values, and this is here equal to 3. And 3 is smaller than P, which is equal to 4. So here we have then this problem that the matrix X transposed X is not invertible. Now we define here our matrix sigma from the array of singular values sigma. And then you see here that we have this column of zeros here. And our matrix sigma transpose times sigma looks then as it is defined here. So here we have this one row of zeros and one column of zeros. Now let's just double check if we did everything right. So we should get now our matrix X by the decomposition of U times sigma times V transposed. And this is actually the case if you compare these two matrices here. And then we have here our function get the beta. So this is for one random draw of the matrix A. So sigma T, sigma P is here supposed to be the pseudo-inverse. First we define it as sigma transpose times sigma. Then we invert here all the non-zero elements. And then we set our matrix A to the pseudo-inverse, and then we draw random rows of A, which delivers then our parameter vector beta according to the formula you can look up in the slides. And then we plot it. And then you get this picture here. So F0, the blue one, is actually the solution when we only use the pseudo-inverse. So here we have now another random sample. So here you see that all of these functions go through these 3 points we have actually observed. But how the function then behaves outside of these 3 functions, yeah, that varies a lot. So this was the first part of our lecture. Now the question arises a bit if maybe not this one sample solution of the beta plus given by the pseudo-inverse of sigma transpose times sigma is not special in a sense, and actually yes it is, and we will see in the following parts into what respect. See you then.